So, after almost 4 weeks, I'm ready to start solving the problems of the next section. It turned out that I needed to study a lot, or rather it started in section 7, where solving the last problems, I realized that I didn't study the section itself to a sufficient depth. So I wanted to be very careful and prove that I was a good student reading section 8. And that gave me problems right away. Here in proposition 14, well, it's not very clear, but it says that two fields are finite Galois extensions of the base field, and that sounded quite right. And then the proof, I knew that was right too, but it turned out basically that I didn't know what a Galois extension was anymore. I had a vague idea, but I didn't know precisely what it meant. So I found my old book on field theory and studied the chapter on Galois extensions. And within 2 pages, I realized that I wasn't ready to study that. I didn't know the theorems that were used in the proofs. So I had to study the chapters 1 and 2, because chapter 3 was the chapter on Galois extensions. Very well. And then soon I realized that I had to read 30 pages with preliminaries before that. I did have the preliminaries for the preliminaries, or prerequisites for the preliminaries, so I was able to do that. Actually, it's a very thorough book with a lot of details explained at long length, not at long length, but very carefully. So it's very nice to get everything explained. On the other hand, it takes a long time because you can't see it by yourself, or maybe you can, but then since there's the proof, maybe you've missed something, so you need to go through the proof detail for detail. So it's not quite easy. On the other hand, it is a complicated theory. But now I feel up to specs. And I also made a lot of explicit calculations, so to make sure that I understood what it was all about. But now to the exercise, the problem 1. So we have an elliptic curve in the Weierstrass normal form, and then we must, only for n equals 2. So all we need to find is an expression for this guy. And we have the complex numbers z, which maps to a point on the elliptic curve. It's not embedded. It's actually modulus that is isomorphic to the curve, lying in the complex, or just write P2, the complex projective plane. And we know the addition form, or rather the doubling formula on the elliptic curve, so we can use that. So if z is mapped to 2z, now I'm speaking American, sorry, then we get twice the point. So this is the point, which in turn is mapped to 2 times the point. Which equals the value at 2z. So we just have to use the addition formula, or rather the doubling formula, then we should get the expression. And here it is. And it's formula 7.2. The x-coordinate of twice x1.y1 is minus. Now, I'll just write the formula as it stands, and then we can specialize it afterwards. This seems right. So, minus 2x1, a equals 4, b vanishes, and we shall differentiate the polynomial. This is f of x. So that gives 12 x squared minus g2 divided by 2 I will just leave that for the time being, I think, and all this squared. Now, what am I looking for? We need to find the this x value. That's what we are looking for. And y1 squared, that's the polynomial itself. So we put it on common denominator, 16. And this gives minus 32 x1 to the 4th plus 8g2 x1 squared and 8 g3 x1. And we continue with this guy squared. And with these long algebraic extensions, doing them on Krita, it's difficult, so I expect to make some mistakes, but now I'll just go ahead and see what I get. And then if it doesn't make sense, I can correct it without recording in my own good time. Now we have 144 minus 32. That gives 112. x1 to the fourth. Minus 16 d2 x1 squared. 1, 2, 3, 4, 5, 6 terms. Now where's the... oh, we have a first order term as well. Does this make sense? Yes, it does. So would 16 divide this? Don't think so. And it doesn't the rest. Well, I think that finishes it. And then we have to use the fact that x1 equals the Weierstrass p function of z. So that we get and then we can either use the square root. Now, it's better just to put this expression, I guess. I think I did mention in one of the earlier problems that one was able to make such formulas. I didn't expect them to be so complicated, though. Well, that's it. Let's try, it didn't take long, to do problem 2 as well. I believe this would be an easy exercise. So I prepared for problem 2 as well. So, Fn is the elliptic function defined in the section. Express f3 as a polynomial in p of z. All right. Now it's defined as a product of first order. Now it's that doesn't even have a number. It's n squared, 9 times the product of where u runs through the third values of a lattice. So all the points of the basic lattice, where 3 times the points give a lattice point, except 0, where it gives infinity. So I wouldn't like to compute all of these values. So I'll do the other thing, use the polynomial we already know, and that was stated in the text somewhere. That wasn't the general one. So we just have to to see. This is the double point, the x value of the double point. Here we have it. Let's rather use this, and that should actually give the same x value. So this should be equal to x1. So the equation is for x equals the Weierstrass of z, that x equals minus 2x plus, and then I forget it, 1/16 12x1 squared four, I guess. So we add x here and multiply. So that gives 3x times 64. Is that 192? And then we reduce it. Oh my God, another factor 4. 800 minus 32, that's 768. So we collect on the left side. Wasn't this 12x squared? It's 12x squared. There we go. So 768 minus 144, that's 624. And 168 d2x squared. We are an x short here. Minus d2 squared. So that's the equation. It's a third order equation, and we do have 9 points altogether, and since the point at infinity excluded, then we have 8 points, so it should be a fourth order. Oh, that's right. A fourth order equation. And then the coefficient to x when it's f3 should be 9. So 9 doesn't divide this number. Damn it. 3 does though. Well, let's just divide by it and multiply. What do we do? Yeah, divide by it and multiply by 9. Oh, we just take 3 out. And then this divided by 3 is 208. So that's the polynomial, so we just have to write it as a polynomial, substitute x equals the Weierstrass function of z, then we get it. And then of course these numbers we need to... Now, I wonder if I've made a mistake, but the method is quite clear, so it's probably the same that when doing these complicated, and on this page as well, algebraic computations on the tablet, I usually make a mistake, but I might be right, who knows. Well, that was those exercises. I did have a feeling that the algebra was erroneous, so I just checked it on Maple to get the right results. And then I checked the last result here with the answers in the back of the book, and it turned out that he only wanted 3 as a coefficient here. So that's the answer. And x is before the constant term here. Now, actually in equation 8.1, he states that the factor should just be n, capital N, whereas in the later unnumbered equations, it has become n squared. So it turns out that they were wrong, and equation 8.1 is the one that is correct. So that's it.